So the planets aren't actually moving in completely circular orbits, they're moving in ellipses, which Kepler first pointed out. And so, in order to make this a complete statement about gravitation, I have to mention about what's happening with regard to Kepler's 3 laws, and what that means for things that are not moving in complete circular motion, but instead elliptical motion. So, Kepler's first law says that the planets move on ellipses with the sun at one focus. So instead of being circular, they instead are elliptical. And by they, I mean their orbits. So the sun would be at some focus. Every ellipse has 2 foci that make it up. If you're talking about a circle, of course, the center that is the relevant thing there is the center of the circle. For ellipse, it's not actually the center that's relevant, it's the foci. And you have the sun being at one of the 2 foci for this elliptical orbit. And you have the object moving in this ellipse. So the ellipse is categorized by 2 different things, that being the semi-major axis, or A, which is the half the length of the longest dimension, and then also the eccentricity. So the eccentricity goes between 0 and 1. The closer to 0 you are, the more circular. The closer to 1 you are, the more stretched out you are, the more approximating a line you are. And if you think about an ellipse, and you squish it to more of a circular orbit, the 2 foci get closer and closer together until they're on top of each other, which would then be the center of your circle. So that is what is actually describing the way the planets move around the sun. And it took a long time to realize this because the orbits are pretty circular. If they were very elliptical, then we would have noticed that a lot earlier, before Kepler was analyzing Tycho Brahe's data. But thankfully he was able to realize this, to notice that these things are moving on ellipses and not on circles. The second law has to deal with how it's moving around in the circle. So, and the second law says that a planet will sweep out equal areas on its orbit in equal time intervals. What does that mean? It means that if you're looking at, say, a point in its travel from here to here, T1 to T2, the area in question is the area from the center of that focus out to the edge. So, moving from here to here, it sweeps out an area from the focus equal to this irregular pizza slice. Okay. So what this law says, as he realized from the data he was watching, that if this is, say, 1 Earth year, then at some other point that ends up being a year over here, that corresponds to the same area as this pizza slice. So that might actually end up being this situation here, from T3 to T4, where this is also 1 Earth year, covering off this part. Or maybe it's actually from here to here, T5, T6, where this would also have the same area as all these different things, and this would be 1 Earth year as well. So what does this actually mean? It means that this time to traverse this amount of orbit is the same as this time to traverse this amount of orbit is the same as this time to traverse that amount of orbit. Or the speeds of the planet as it moves around are different. The speed here is slower compared to here, and this is in between those 2 speeds. So the further you are from the planet, so the further you are from the sun, pardon me, then the slower the planet is moving. The closer you are to the sun, the faster the planet is moving. And we can look at this by analyzing how the force is acting on the planet in question. So, the planet, put the sun back where it's supposed to be, we have a planet over here. The gravitational force is directed towards the center of the sun. So that is moving in this direction here. The velocity, the tangential velocity, is this way. This might be a little bit hard to see for the point I just picked right here, but this velocity is not perpendicular to this gravitational force. So unlike the example I said before of the circular motion, where the gravitational force is always perpendicular to the tangential velocity, and therefore only change direction and not the speed, this is not the same case. We now have a situation, we draw it over here so it might be a little bit more obvious, where the gravitational force partly lies along the orbit of the ellipse if you break it down into components. So I have my gravitational force here. If I set up an x and y axis right here, then I would have an actual gravitational force pointing this way, and also part of it pointing this way. Which means, since the gravitational force would be in the same direction as the velocity direction, that the acceleration it experiences makes the velocity increase. So you have a positive acceleration with this positive velocity, if we're assuming that this direction is positive, which makes it speed up as it goes this way. And it keeps on speeding up until it gets over here. So someplace in this orbit, we have the speed now tangentially moving in this direction, and the gravitational force still pointing back to the sun. Now, the portion of the gravitational force that lies along the orbit is in the opposite direction of the tangential velocity, which means that the speed ends up slowing down. So, once you start here, it increases the speed, increases the speed, increases the speed, increases the speed to here, where it is, at this point, perpendicular. You have a relationship between the orbit, the tangential part of the orbit, and the gravitational force, which means that it is just changing direction here, it's not changing speed. So, and it still ends up, and then once that happens, then you end up starting to decrease the speed as it moves around until you reach the opposite portion, where again they're perpendicular, and it can start speeding up the object again. So the reason why it sweeps out equal areas in equal time intervals is because of the gravitational force it's experiencing, and the fact that part of that force is directed along the orbit, which can speed up or slow down the motion of the object. So that was actually number 2. So number 3 talks about different distances and different speeds of orbits. And what it says is that the square of the orbital period of an object, well, of a planet, if we're talking about the solar system, is equal, well, proportional to the cube of the average distance of that planet from the sun. Okay. So, if we assume, for argument's sake, that this is a circle, which we take an average distance for the ellipse and we can make that ellipse into a circle, then we know that we have the circular motion that we've been talking about. So, the gravitational force is equal to the centripetal acceleration times the mass that it's experiencing. So we have g times m sun times m planet divided by the distance between the sun and the planet, quantity squared, is equal to the acceleration centripetally times the mass of the planet, times v squared over that distance. So the mass of the planets would end up canceling. You end up canceling one factor of r here, that factor is gone. So now you have g m sun over r is equal to v squared. Now if we're talking specifically about an orbit, and we want to know the orbital period, okay, a period would be the time it takes to go from one point to go all the way back around. So that would be one complete orbit. So the distance you go, if you're talking about a circle, would be the circumference of that circle in a time of one period. Now, distance divided by time is a velocity, and so the velocity along the circle that we were talking about here would be the circumference divided by the time. So, I can take that and put that in. If I say v is equal to 2 pi r divided by the period, which is capital T, then g m sun over r is equal to 2 pi r over t quantity squared. And so rearranging this and solving for t, I notice that I have t is equal to 4 pi squared over g m sun, t squared, pardon me, times r cubed. So this is 4 pi squared over r squared over 4 pi squared r squared over t squared. Rearranging things, I have t squared is equal to 4 pi squared over g m sun times r cubed. And which is exactly what Kepler realized when he looked at his data. He noticed that this effect was seen, and we can say why, because of what Newton has told us about circular motion and the use of forces. So this says that a planet that is further from the sun than we are will take longer to orbit around the sun than we do. So anything that's beyond us, Mars, Jupiter, Saturn, Uranus, Neptune, all of those planets, regardless of their mass, will end up orbiting at a slower speed because they are further away from us. They will take longer to complete their orbits because of that physical distance. And those are Kepler's 3 laws, and we can see how they are explained by the use of the gravitational force by the arguments of centripetal acceleration and circular motion.